Hey y'all, it's Miss Miller again. I just came up with another set of notes for you all to basically show you a little bit more of what's going on and some clarification on some things. I went through and took the unit test so that I kind of knew what was going on, and so I could make sure that you were better prepared. Feel free to use your notes on the unit test. Why not, you all? This is supposed to be helping you to learn. That's the point. It's not, oh, well, you don't get it. It's how are we making sure that you're doing what you're supposed to be doing? Are you following what you're supposed to be following? And this is more feedback for me to see where I need to clarify. I've gotten quite a few questions on some of these things on these second round of notes. And so that's why I wanted to go through and help you all to be able to kind of clear up some things and go through some extra things that I don't think I clarified very well. So here we go. Probability is the chances of an event occurring. It's always out of 100. It's never more than 100%. That means it can never be more than 1.00. It can never, so sometimes the weathermen will joke, oh, it's like 150% chance it's raining. In math, you will never ever see a probability problem that goes over 100%, or if it does, then something's wrong, and it's probably trying to get you to figure that out. So make sure that you're paying attention to that. There's also two types of probability. There's both experimental and theoretical. Experimental is what actually happens. So if you sit there and flip a coin 500 times, what's it going to look like? It may be 400 times it landed on heads and 100 times it landed on tails. That's what's actually occurring. So then if you're going to base your guess on what's going to happen next, and it's telling you to base it on the experimental data, it wants you to base it on that data. It wants you to base this is what's happening. But if you're talking about basing it off of theoretical data, that means what would happen in a perfect world? Well, in a perfect world, if there's two choices, it's 50% going to land on heads and 50% going to land on tails. The theory, get it, theoretical, the theory is that if you do it enough, that it should reflect that data. So if you do it 500,000 times, it should be 250,000 heads and 250,000 tails. Obviously, when you're doing it, that doesn't always happen. But theoretically, if you do it forever and ever and ever, an infinite number of times, it should work out where it's 50% heads and 50% tails. Okay. So experimental is based on the exact data of what occurred. Theoretical is based on what should happen in a perfect world. Okay, if we are trying to compare likelihoods to compare which is more likely to occur, you use a common denominator to be able to compare those. So, like if I was trying to decide if something was more likely, it had a probability of 2/5 of occurring versus 4/9 of occurring. If I'm trying to figure out which is more likely, okay, I can either create common denominators to compare them and figure out that 20/45 is more than 18/45, so that's more likely to happen, or convert it to percents. So to convert to a percent, remember, we're doing numerator divided by denominator. So we'll do 18 divided by 45 to get me 40%, or 20 divided by 45 to get me 44%. Well, the 4/9 probability is more likely because it's a higher percentage, okay? Outcomes. Okay, so there was some clarification. There was a couple of problems, hint, 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 that talked about coin flipping. Okay, and it talks about 3 times it's going to flip a coin. The chances of landing theoretically on heads or tails based on what happened before does not change. Just because it landed on heads the first and second time doesn't mean it's more likely to land on heads the third time. Okay, so if you look, when you flip a coin, you have two choices, heads or tails. Okay, that's your first flip. Then, if you landed on heads, the probability is still that it can land 50% on heads or 50% on tails. So that's your second flip. I showed that as well with if it landed on tails the first time, it still has that same likelihood. So the total number of paths on here are 8. So your probability, your denominator is going to be out of 8. Okay. When you list them, make sure you have the correct outcome. Okay. Make sure you list that when it talks about, did Sally do it right or whatever, make sure that there are 8 different opportunities or 8 different choices. I rewrote it on my last page over here because I thought it needed a little bit more clarification. This is what it looks like when you write out the sample space. Okay. Just heads, tails, heads, tails, heads, tails, all of that is not really clarifying the order because the order matters in this case. What happened on the first one? It wants a specific result. What happened on the second flip? It wants a specific result, etc. Then it can say, if you flipped a coin 3 times, what are the chances of it landing all the same way? Well, if it landed all on heads or all on tails, both of those make it true. It would be 2 out of 8. Okay. So let's go back up here. Okay, sampling. So this kind of gets into generalizing what your data is saying. Okay, general statements need to be based on what was exactly surveyed. So if it talks about surveying 5-year-olds in Miss Lama's class, okay, we can't say that that is an accurate representation of the entire school. Okay, we have to be specific that if, the favorite animal in Miss Lama's class is a dog, we can't say that 50% of the school likes dogs because it's just taking too specific of an example. Whereas if we say like 50% of Miss Lama's class likes dogs, then great, that's example. 50% of the first grade, even, or what did I say, 5-year-olds? I don't know. Clearly, I have B on my mind. Sorry. We have to be specific about who that random sampling represents. When we're trying to change from the sample number to the general public number, if it was an accurate representation, we just do that cross multiply and divide. We're trying to find whatever's missing. If we know how many real people there are in the general public or whatever, or in the school, in our sample, if it was 10 out of 25 that liked dogs, and 10 out of 25, and we randomly picked kids from the school or whatever, that it was more accurate, there's a V word that I'm looking for. I don't remember what it is. Sorry about you all. I'm brain dead. It's nap time. I'm supposed to be napping with children. So here, sorry, you all. Thank you. So you would cross multiply and divide to figure out what it is in real life. Okay. And we can use that because of equivalence. So we can make equivalent fractions there to represent what's going on. Sorry. Okay, replacement. So this is kind of talking about cards. If you are drawing cards consecutively, that means in order. If you are drawing a card and then putting it back in the deck before you draw another card, then the denominator will stay the same. So that's what it looks like with replacement. You replaced it back in the deck. So our denominator, our possible choices are exactly the same. They're still 52. But if we don't replace it, we draw a jack and we keep the jack. Now there's only 51 cards left in the deck. So in that case, their individual probabilities would be 4 out of 52. But if we're talking about no replacing, then we would have to subtract 1 from our denominator to multiply 4/52, and means multiply, times 4 over 51 to get 16 over 2652. Enjoy that. Which is 0.603%. Okay. If we replaced it, we drew our jack, we put our jack back in, and then we were looking to draw a 10, our chances go down, okay, because there's more cards to choose from. So in that case, it's only 0.592%, not 59.2%, but 0.592%, okay? If you have any questions on anything on here, please let me know. Comment that this helped you or didn't help you if you have clarifications on Google Classroom so that I know exactly what's going on and how to help you all. Thank you all so much for listening to my spiel. So I'm trying to figure it out. You're welcome. Here we are, and goodbye.